We're talking about the limits involving infinity. Let's start with some simple examples. We want to know the limit of 1 over x as x goes to 0 from the right side. Well, let's imagine when x approaches to 0, x is a very small number. For example, x is equal to 0.01, and then 1 over x becomes 100. So as x gets closer and closer to 0, and 1 over x gets bigger and bigger and without any bound. Therefore, that limit should be positive infinity. And now if you look at the same limit, but x goes to 0 from the left, you can use the same idea except the sign is now negative. Therefore, the limit should be negative infinity. Here we have two more examples. 1 over x squared, again, limit going from both sides. Well, the first one going from the positive side, the limit is infinity, exactly the same argument as before. For the second one, the limit, well, is now positive infinity because x squared turns everything to be positive. Okay, so it is a positive infinity for this one. And here are the graphs for the two functions. First one is y equals 1 over x right here. Second one is 1 over x squared. So here y equals 1 over x, as you can see, the limit from the right approaches to infinity here, right here. And then the limit from the left goes to negative infinity. On the other hand, if you look at 1 over x squared, then the limit goes to infinity from both sides. One intuitive way to think about this is to think about these limits as 1 over 0. I know 1 over 0 does not make sense, so this is not rigorously, mathematically rigorous, but it helps you to understand. Basically, 1 over 0 is equal to infinity or minus infinity, depending on whether that denominator term is positive or negative. Let's use this principle to look at more examples. So here we have another fraction, and x goes to 3 from the left, and then you take x minus 3 to the third power. Well, this is a something over 0 type, so the top is the limit is equal to 6 because 2 times 3 is 6. The bottom, the limit goes to 0, but it's actually a negative number because x is less than 3. Notice that and when x is less than 3, x minus 3 is negative. And if you take the third power, it is still negative. So the bottom should be 0, but with a negative sign. Therefore, this limit should be equal to minus infinity. Let's just do another one very quickly. We have another fraction, x goes to minus 2 from the positive side. So the top approaches to negative 4 because 2 times minus 2 is minus 4. The bottom goes to 0, but it actually goes to 0 with a positive sign because x is bigger than minus 2. Therefore, the answer should be equal to negative infinity because you have a negative sign on the top and a positive sign on the bottom. So, in all these examples, the limit of the function is either equal to infinity or minus infinity as x approaches to a number, either from the right or from the left. And the picture typically looks like this, either goes to infinity or minus infinity, okay? This leads to the definition of a vertical asymptote. We say that x equals a is a vertical asymptote of a function fx if one of the following is true. Either the limit from both sides is equal to infinity, or from the right is equal to infinity, or from the left is equal to infinity. Or the limit of the function from either from both sides or from right or left is equal to minus infinity. We have seen some examples in the previous slide, but let's just take a look of the kind of general pictures from the left, from the right, and when the limit is equal to positive infinity, or from the left or from the right when the limit is negative infinity. Let's look at the example that we did. In the previous slide, we showed this limit is equal to minus infinity. Therefore, by the definition, x equals to 3 is a vertical asymptote for this function. In general, if you have a rational function, to find the vertical asymptotes, you look at where the denominator becomes 0. And then you verify that the limit is indeed infinitive or minus infinitive. In this case, this is the only vertical asymptote. So far, we have talked about the limits for which the function f(x) goes to infinitive or minus infinitive. Let's look at the limit when x goes to infinitive. Let's start with these two examples. The limit as x goes to infinitive of 1 over x. Well, when x goes to infinitive, x becomes bigger and bigger. Therefore, 1 over x gets smaller and smaller and arbitrarily close to 0. Therefore, it is easy to imagine this limit should be 0. If you look at the limit of 1 over x the third as x goes to minus infinitive, the same argument works. This time, x to the third is a negative number, so this fraction is a negative number, but it still gets closer and closer to 0. Therefore, the limit is still equal to 0. These two examples do give us a general principle as before, which is this time it says 1 over infinitive equals 0. What this means is that if you have a limit for which if you have a fraction and then take the limit, if the top goes to a fixed number like a 1 and the bottom goes to infinitive, then the limit of the fraction should be equal to 0. If the bottom goes to minus infinitive, the same result is still true. This should be thought about as a intuitive way to remember this, but it's not a rigorous mathematical expression. Let's use this principle to calculate examples that are slightly more complicated. Here we have a rational function. To do this, you can take out the highest degree term from top and from bottom, and then that will reduce to limits like this. All right. In this case, the highest degree terms are 2x squared on the top and 3x squared on the bottom. Therefore, the limit becomes the following expression. So notice that if you take out 2x squared, then you have 1 left here, and then you have a 3x over 2x squared here. And then on the bottom, you take out a 3x squared, and then you have 1 plus 8 divided by 3x squared. And then you do some simple cancellation. X squared cancel with x squared. So you have 2 and 3 here, and then x cancel with x squared, so you have 2x on the bottom, and then here it remains to be 3x squared. And now you can apply these principles. So notice 2x goes to infinitive, therefore this portion should go to 0. So the top goes to 2 times 1 minus 0, and the bottom, again, this part goes to 0. So the bottom should go to 3, therefore the answer is simply 2/3. This example also shows a general principle for computing limit of rational functions. That is, you can look at the highest degree terms and then simply throw away the remaining terms. And that will give you the same limit as x goes to infinitive or minus infinitive. And the reason why you can do that is exactly because of what we did here, because when you take out the highest degree terms, the lowest degree terms always contributes 0. So let's redo this problem using that idea. So basically you throw away the lower degree terms and you simply get the following, and then cancel out x squared, and then the answer is 2/3. Very simple. Let's look at another example of a rational function. So again, we have a rational function. Here the degree of the top is 5, the degree of the bottom is 2. We can use this principle that we just explained. You throw away the lower degree terms and keep those 2 highest degree terms. Therefore, you simply have 2x to the 5th on the top, 3x squared on the bottom, and after you cancel out, you have x to the 3rd on the top. When x goes to infinitive, x to the 3rd goes to infinitive. Therefore, The answer is infinity. Let's look at just one more example of a rational function. Here again, you can throw away the lower degree terms. So on the top, you just you have 2x squared. On the bottom, you have 3x to the fifth. I'm going to leave it to you to convince yourself that the limit is 0. Now these three examples are all about rational functions, and we can make some observation from here. If the degree of the top is bigger than degree of the bottom, which is our example here, so the degree of the top is 5, the degree of the bottom is 2. In that case, the limit as x goes to infinity is either infinitive or minus infinitive, depending on the sign and depending on whether x is going to infinitive or minus infinitive. Okay. Now, if the top has a smaller degree than the bottom, like example here, so then the limit should be 0. Basically, you go through the same idea, and then after you cancel out, the bottom has a x to the some power. So the bottom goes to infinitive, and the top is a fixed number. So the limit should be 0. If the top and the bottom have the same degree, then just like this example here, then what happens is that you're going to cancel out those x to the nth power here, and then you just look at the coefficients of the leading term. So the answer is just the ratio of the coefficient, which I denote by a over b. Okay. Let's look at a few more complicated examples as x goes to infinitive or minus infinitive. Here we have a square root, and then divided by some polynomial, in this case just the 3x. Well, you can use that same principle to drop 10x here, because x squared is the leading coefficient. So this should be equal to square root of x squared over 3x. And then this is just equal to absolute value of x. Now, because x is approaching negative infinity, absolute value of x is actually equal to negative x. Okay. Now, if you cancel out the x here, then this becomes just the minus 1/3. So the limit is minus 1/3. Okay. Let's look at another example. This is a trickier example. X goes to infinity, square root of x squared plus 2, and then minus x. Okay. Notice the first part goes to infinitive as x goes to infinitive. And this part also goes to infinitive. So you have a kind of infinitive minus infinitive. And in general, that's undetermined. It's you don't know what that should be. It could be any number. Could be infinitive, could be minus infinitive, or a finite number. What you can do here is to use the technique of multiplying by conjugate of a square root expression. So think about this as a fraction. So the same expression divided by 1. Now you multiply top and the bottom by the conjugate of this. In other words, you multiply by the square root plus x. Now here on the top, this is of the form a plus b times a minus b. And then apply the formula that should be a squared minus b squared. In other words, it's a square root of square, which is x squared plus 2, minus b squared, which is just x squared. Okay, and we keep the bottom. So now square x square cancel each other, so you just have a 2 left. Now we have a fraction, a fixed number, and the bottom goes to infinity because we have a summation of 2 expressions. Both these two go to infinity. So the bottom goes to infinity, therefore this fraction should approach to 0. Let's just look at one more little trigonometric function, cotangent x. Well, for that, it's best to express the function in terms of sine and cosine. So cotangent is cosine over sine. Now, when x approaches to 2 pi, cosine x approaches to 1 because cosine 2 pi is 1. Sine x approaches to 0 because sine 2 pi is 0. So you basically have 1 over 0. Well, that should be infinitive. But let's look at whether it's a plus or minus infinitive. X approaches to 2 pi from the left. That means sine x is actually a negative number. So it goes to 0, but it's a negative. Basically, this is in the fourth quadrant. This angle is in the fourth quadrant, so sine should be negative. Therefore, the answer should be negative infinity. Now, parallel to the concept of vertical asymptote we just defined a moment ago, we can define horizontal asymptote. So here's the definition. We say y equals L is a horizontal asymptote of the function if, as x goes to infinitive, fx approaches to L, or when x goes to minus infinitive, fx approaches to L. Here are the pictures. This is the picture when x goes to minus infinitive. Fx approaches to L. As you can see, fx gets closer and closer to L, so we say this is a horizontal asymptote. And here is the picture when x goes to plus infinitive and fx approaches to L. So these are the two possible pictures of horizontal asymptotes. Let's look at the example that we did. Again, we showed that this limit is equal to 2/3 as x goes to infinity. Basically, remember we look at the leading terms and then the highest degree terms and look at the coefficient, and that's 2/3. So because of that, we say y equals to 2/3 is the horizontal asymptote. And if x goes to minus infinity, the same limit is true. So this is the only horizontal asymptote. Let's look at an example determining both vertical and horizontal asymptotes. So here we have a rational function. To determine vertical asymptote, as we said earlier, you look at where the denominator is 0. So you solve for x plus 2 equals 0, and therefore x equals to minus 2. And it's easy to check that the limit is indeed infinitive or minus infinitive. We're going to see that in a moment. Now, let's determine the horizontal asymptote. We need to determine the limit of fx as x goes to infinitive and when x goes to minus infinitive. Well, they're both pretty standard to be determined. Basically, you throw away the lower degree terms, and then you just have 2x over x, and then the answer equals to 2. That's when the limit, when x goes to minus infinitive. The limit when x goes to plus infinitive is the same thing. So that means the only horizontal asymptote is y equals to 2. I would like to give a remark how these asymptotes can help us to better understand the graph of a function. So here, if we know that x equals to minus 2 is a vertical asymptote, but we can look deeper to understand the limits as x goes to minus 2 from the left and from the right. All right. The limit from the right should be equal to minus infinity because the top goes to 2 times minus 2 minus 1, which is a minus 5, so it's a negative. The bottom is a positive. It goes to 0, but it's a positive, so it should be minus infinity. And the same argument shows the limit from the left should be positive infinity. And that should help you to understand the graph near x equals to minus 2. Let's give it a try. So here, what you should do is to draw the horizontal asymptote and vertical asymptote. So horizontal asymptote y equals 2 and vertical asymptote y equals minus 2. All right. The limit as x goes to minus 2 from the right is minus infinity. So we're talking about it near here, okay? And then look at the horizontal asymptote. The limit as x goes to infinity is equal to 2. So that means we're talking about the graph that near y equals 2. So that gives us some idea what the graph should look like. So that means the graph should start from around here and then approach to 2 as x goes to infinity. Therefore, the graph should roughly look like this. And now if we look at the limit as x goes to -2 from the left, we know the limit is plus infinity, so it's around here, and then as x goes to minus infinity, the limit is equal to 2. So we should expect something like this. All right, the actual graph looks like that. So we're pretty much the same as the actual graph.